Hello everybody. We are continuing with chapter 4 about general vector spaces. And so we are now in section 2. So 4.2 is all about subspaces. So that's going to be an important concept. Chapter 4 has actually a lot of important concepts. But this next one is subspaces. So don't forget, we previously talked about real vector spaces. So now we're going to be talking about subspaces. So the whole point of this section is that we often have some vector space of interest that's actually contained within a larger vector space whose properties that we already know. So we want to be able to recognize when this is happening, and we want to show how the properties of the larger vector space can be used to obtain properties of the smaller vector space. And this chapter is going to have, or I should say this section will have, a variety of important examples. So what are we dealing with here, folks? We're dealing with a space within a space. So before we talked about how to recognize a vector space, well, now we're also going to be talking about the subspaces within that vector space. So think of it as a space within a space. So of course we always have to go ahead and make sure that we have some important definitions out of the way. So your first one is definition 1. A subset W of a vector space V is called a subspace of V if W is itself a vector space under the addition and scalar multiplication defined on V. So remember all those axioms from last section? There was 10 of them. And we used them to determine whether or not a set V was actually a vector space. Well, now we're going to be looking at some of those axioms to determine if a subset W is actually a subspace of a vector space V. But the good thing is we're not going to have to laboriously go through all 10, so you're going to be happy about that. So let's check out how this works. So here we have a reduced amount of axioms that we actually have to look at. So if we're looking at this space within a space and we want to know, okay, is this subspace a vector space as well? Well, the ones that we do have to look at are axioms 1, 4, 5, and 6. You can assume that the rest of them are inherited and that they do hold true, but these axioms 1, 4, 5, and 6 will still need verification. So we'll look at these in detail here. So if we want to verify that W is in fact a subspace of V, we need to verify that it is closed under addition and scalar multiplication. So I hope right away immediately that you are recognizing that those in fact are axioms 1 and 6. So don't forget your axiom 1 and 6. So axiom 1 was what? Your addition, don't forget. And your axiom 6 was your scalar multiplication. So we have to verify those for the subspace W. So just looking at this diagram, I really like this diagram because here it kind of shows quite a few things. So look at this outer blue space here, this vector space V. So here it kind of gives you a visualization that here is this subspace W, and it's a space within a space, obviously, so W is within the vector space V. And so we have to verify that W is itself a vector space. And you'll notice that it's really, really important that we do have to prove these axioms 1 and 6 hold, and that that W is closed under addition and scalar multiplication, because this diagram actually shows an interesting thing here. So it says the vectors U and V are in W. So here's U, if you see it, this blue one right here, and here we have V. So those are, you can see they're within W here. But interestingly, look at this. It says, but the vectors U plus V and KU are not. So here we have U and V, and if we added both of them together, depending on what they are, well, actually their result here, this U plus V, see this dot right up here? It's actually outside the scope of W. And then this could also happen with our scalar multiplication. So you can see KU, it's extending beyond W into V. So, you know, we can't then say that W itself is a vector space, since these two things don't necessarily hold true all the time. So we are trying to prove that the subspace W is in fact its own vector space. And this diagram is showing you that it might not always be the case, so that's why it's important that you have to prove it. So axiom 1 and 6 are going to once again be predominant in importance for verifying this. So please make sure that you remember your axiom 1 and 6, right? Okay. So here it leads to our next important theorem for this chapter, is that you have theorem 4.2.1, the subspace test. So if W is a non-empty set of vectors in vector space V, then W is a subspace of V if and only if the following conditions are satisfied. And that is A, if U and V are vectors in W, then U plus V is in W. And B, if K is a scalar and U is a vector in W, then KU is in W. So these are your axioms 1 and 6. So interestingly though, what's really cool is that if axiom 1 and axiom 6 hold in W, then axioms 4 and 5 hold in W as a consequence, and they don't need to be verified. So if you can prove this axiom 1 and your axiom 6 for W, then that means, just realize, then that means axiom 4 and 5 hold too. So these are really the ones that we need to concentrate on, is axiom 1 and 6. So just realize that. Not as much work, certainly, as before. So if axiom 1 and 6 hold, we're going to assume then that axiom 4 and 5 then hold too. And then one other point I just wanted to clarify really quickly is that axioms 2, 3, 7, 8, 9, and 10, those are therefore inherited from the vector space V. So we don't have to worry about verifying those. So one other thing that I wanted to point out, actually two things, is just realize that this is the subspace test. So if you see that referred to in a problem or further in the text, then you know what that means, that you're verifying your axiom 1 and 6. And then the other thing that I just wanted to make sure that you recognize too, and this is assuming that W is a non-empty set of vectors. So that's a natural assumption there. So one particular subspace that you should always know, because we see its analogy in many other concepts that we've learned, but that is the zero subspace. So I want you to note that every vector space has at least two subspaces, and that's going to be itself and the zero subspace. So if you have a vector space, it's going to have the zero subspace and itself at least. So just taking a look at what the zero subspace is, it's if V is any vector space, and if W, not here, that's going to be the subspace, equals 0, the zero vector there, is the subset of V that consists of the zero vector only, then W is closed under addition and scalar multiplication, since the zero vector plus the zero vector is going to equal the zero vector. And here you have any scalar k times the zero vector, it's going to equal the zero vector for any scalar k. So in this instance, we're going to call W the zero subspace of V. So keep in mind that you will have the zero subspace for any vector space. All right, so I like example 2 because I think it's good in helping to visualize things. So if you look at example 2, W is a line through the origin of either R2 or R3. So if you look closely at this, in this first picture here, we have this line W. And if we add any two the vectors U and V along W, then it's going to produce another vector U plus V that's also on W. So we would say that W is closed under addition, or axiom 1. So like I said, it's a line through the origin. And then if you look at this second picture, if we multiply a vector on the line by a scalar k, that's going to produce another vector along the line W. So here we have U, and then it's multiplied by a scalar k, so here we get KU. So this could be anywhere along the line W, depending on how big or small k is. But we'd say that W is closed under scalar multiplication, or our axiom 6. So here we see a similar thing in example 3 when we're talking about planes. So here W is a plane, and U and V are vectors in that plane. And once again, make sure that you note that this plane W is going through the origin of R3. So if U and V are vectors in plane W through the origin of R3, then we can see that U plus V and KU also lie in the same plane W for any scalar k. So you can see that from this particular picture here. So here we have U, we have V, and then here would be U plus V. So certainly this U plus V would be adjusted depending on how big or small U or V might be. And then here we have U, and then we have multiplied times the scalar k, so here's KU. And these all reside within the plane W. So once again, we would see in this instance that W is closed under addition and scalar multiplication. So section 4.2 gives us handy table 1, and this is the list of subspaces of R2 and R3 that we've encountered so far. So you'll see that subspaces of R2 that we've looked at is obviously the zero subspace. We've looked at lines through the origin. Certainly R2 is a subspace of R2, because remember, there's at least two subspaces. It would be the zero subspace plus the space itself. And then here for R3, we've got the 0 subspace, we've got lines through the origin, now we've got planes through the origin, and R3 itself. So handy little table there that I'd recommend bookmarking. But we can't just get into the habit of thinking that everything qualifies as either a vector space or a subspace, because guess what? We are going to encounter those situations where a subset is not a subspace. So if you look at example 4, which is interesting. So here in this instance, W is going to be the set of all points, x and y, in R2, for which x is greater than or equal to 0 and y is greater than or equal to 0. So I like this figure that they have here because you can see that since x is greater than or equal to 0 and y is greater than or equal to 0, that you're really talking about this quadrant 1 here in gray. So see how they have it kind of shaded in gray? Because this is the only quadrant here that's going to fit the bill where both x and y are greater than or equal to 0. So just wanted to point that out, so make sure that you check this figure out. So from this figure, I think it's kind of easy to see that, whatever x happens to be or whatever y happens to be, as long as they're both greater than or equal to 0, W is going to be closed under addition. So x and y are going to be greater than or equal to 0. They're all, and in adding x plus y, they're all going to end up, here in this particular quadrant. So, W is closed under addition, but if you notice, what's interesting is that W is not closed, so not closed under scalar multiplication. So don't forget, that's your axiom 6. And so what if in this instance, k happened to be -1? So here, if you had a vector v11, so v itself would lie in W, right? Because, its x and y are 1, and those are obviously greater than or equal to 0. So obviously, v would lie here at 1, 1. But if you had a scalar k that ended up being -1, so that if you multiply -1 times v, you'd have this point -1, -1. And so obviously, that would fall over here in quadrant 3. And so that's not in W, is it? So in this instance, W is certainly a set of points, but guess what? It is not a subspace because it failed axiom 6. So it is not closed under scalar multiplication. So just realize you are going to have to verify each of these things because, not every set is a vector space or not every set given is a subspace. So you do have to check. So you also do want to take note of this example 5 because this is talking about symmetric matrices. So it's talking about subspaces of M and N. So we usually denote our matrix spaces by the big M here, obviously, and then this is going to indicate the dimensions of that matrix. So just wanted you to realize that you'll kind of want to make note of this because there's certainly going to be some problems about this, but realize that the sum of two symmetric n by n matrices is symmetric and that a scalar multiple of a symmetric n by n matrix is symmetric. Thus, the set of symmetric n by n matrices is closed under addition and scalar multiplication, and hence is a subspace of M and N. So this property you're also going to want to take note of for sets of upper triangular matrices, lower triangular matrices, and diagonal matrices. Those are all going to be subspaces of M and N. And so just realize, take note, when you're looking at this example, you're going to want to think about this is a set of symmetric n by n matrices. And then they're also talking about the sets of the upper triangular matrices, lower triangular, and diagonal matrices. So good one to kind of keep note of. So example 6, though, is different because you're going to be faced with a subset of n by n matrices that is not a subspace. So we saw before those other ones were subspaces, but they were very particular types of matrices. But here this gives an example of a subset that is not a subspace. So just realize a set, whatever it's giving you in a problem, a set doesn't necessarily, it's not necessarily a subspace or a vector space. So like I said, you got to determine if it is or not. So in this particular example, here we have the set W of invertible n by n matrices. And it's not a subspace of n by n matrices, and because it fails on 2 counts. So it's not closed under addition, and it's not closed under scalar multiplication. So I do want to make sure that I bring to your attention that you're always wanting to look for the details. So this set W, what is it telling you about this set? It's telling you that it's talking about invertible matrices. It's also giving you the specification that's an n by n matrices, and we know those to be square matrices, right? So always be paying attention to the details. So here, we can find examples where this set W is not closed under addition or under scalar multiplication. So we're going to be able to say, hey, you know what? Set W is not a subspace. And so what they're giving you for consideration here are these 2 matrices, U and V. So here they have U as matrices that look like this, and here we have V equals this one. And so what do we got to prove? Well, we got to show that axiom 1 and 6 do not hold. So here, if you look at, okay, if we look at axiom 1, and that's going to be our u plus v. Well, look at this. If we add these two together, here we've got 1 plus negative 1. Okay, that's 0. We've got 2 plus 2. That would be 4. Then we've got 2 plus negative 2. That's going to be 0. And then we have 5 plus 5. That'll be 10. So what's the problem with that? Well, look at this. We've got a column of zeros. Well, that's telling us that this is not invertible. Because remember, if a matrix is invertible, it means that its determinant is not equal to 0. So if invertible, the determinant does not equal 0. But here we'd see, okay, AB minus BC here. Well, you'd end up getting to 0 for that determinant, right? Because we have this column of zeros. So this isn't going to fit the bill. Because remember, the set W is a set of invertible n by n matrices. So here, under addition, this doesn't hold. Then if we look at axiom 6, which is our KU, well, look what happens here. What if K happens to be 0? So if we have 0U, obviously, what are we going to get? We're going to get this 0 matrix here. Well, that doesn't have a determinant that does not equal 0, so this is invertible as well. So this one's not going to fit the bill either. So in this case, we would say, you know what? W is not a subspace. So go fish, try again. It's not going to be this one. Okay, let's look at another example 11. So don't forget, when you are applying the subspace test, what are you doing? You're trying to see if axiom 1 and 6 holds. You're trying to see if the subspace is, or the set, I should say, is closed under addition, or if it's closed under scalar multiplication. And if both of those hold, then yes, indeed, it is a subspace. So here we have some different matrices, and they're saying, well, are they a subspace of M22? So here we have in part A, we have the set U consisting of all matrices of the form. So here it's just calling it a set U right now. And we're trying to determine if the set U is actually a subspace U. So we're going to have to do the subspace test. Okay, so if we're looking at it and trying to see if it fulfills the subspace test, we have to realize that we're going to have to kind of prove this, obviously. So we're going to say let A equal A0 to AB. So this would be a very generic form of this matrix form here, right? Because we're trying to prove this. And then here we're going to have another matrix, B, and that one's going to equal C0 to CD. Now I will say, if you get problems and you're having to prove these things, you're going to have to get a little creative. You might have to, obviously provide examples possibly in more generic terms, or you might actually come up with very specific matrices, and we'll see that in a second. So here let's have these two matrices here. And so they do have this form that fits the set U. So here, what do we got to do? We got to prove axiom 1, which means that A plus B equals this type of form. So let's see how this works out. So A plus B then would be A plus C. Obviously 0 plus 0 would be 0 here. And then we'd have 2 times A plus C, because we pull out that 2. And then we'd have here B plus D. And so we would be able to say that this particular matrix is in U because it fits this form. And we would say that then that U is closed under addition. Because here, A plus C, no matter what A and C are, it would fit the form of X here. B plus D, whatever they happen to be, they would fit the form of being Y because they could be added together. Here, whatever A and C happen to be, it would still fit this form because it's the same as the entry here. So these would be closed under addition. So this would be axiom 1, and that would be closed under addition. And so let's go ahead and look at then, obviously we want to look at our scalar multiplication, right? So then we'd want to look at Ka, right? So what would Ka be? Well, that one's pretty easy. So we'd have Ka, we'd have 0 here, we'd have 2Ka, and then we'd have Kb. And so once again, this would fit this form, for all real, for these real numbers, A, B, and K. And so we would be able to say then that this is closed under scalar multiplication. So here, yes, we would say that the set U, actually, yes, it is a subspace of M22 here. But we have this next example here in part B. So here's why I think this example is interesting, because here we're kind of putting these matrices in terms of kind of generic terms A and C. It doesn't really matter what they are, because we're showing that whatever A, B, C, and D, and K are, it's going to fit this form. But, sometimes it's not easy to do that, easy to show that, because you might have, a situation like this where it's not, as readily visible. So basically, you have to think to yourself, okay, if I'm proving, or if I'm trying to show that axiom 1 and 6 hold, well, really, to be able to determine whether or not a set is a subspace or not, really, all I need to really do is show one example where those things don't hold, and then I'll be able to say, you know what, this set is not a subspace. So it's kind of easier to sometimes come up with an example that shows that the set is not a subspace, instead of trying to find the expressions to show that, for all cases it will hold for axiom 1 and 6. So if I can just find one example where it doesn't hold, then you know what? I'm good to go. So for this one, they do show you that they did come up with an example, because they said let A equal 1, negative 1, 0, 0. And so what's happening here? So we see that if we actually did use this matrix A and used it to calculate this expression, we'd have 1, negative 1, 0, 0 times 1, 2. And we would see, in fact, that we'd have 1 times 1 plus 0 times 2. Well, that would give us 1. Then we'd have negative 1 times 1 plus 0, and that would be a negative 1. So this particular example of a matrix would fulfill this expression. However, we don't want to assume that just because this one particular example of A fit, that doesn't mean they all will, because then they go on to show you that, okay, well, you know what? If we have a multiple of A, like 2A, is that going to fit this form? So here, 2A times 1, 2, that one's going to equal then 2, 0, negative 2, 0 times our 1, 2. That is going to equal then 2, negative 2. So this one, if we look at this, this is not going to fit the bill, because here under scalar multiplication, where we took 2A, it's not going to fulfill this form. So we would say that this is not closed under scalar multiplication. So in this instance, the set W is not going to be a subspace. Now, we're not going to go through and prove it, but I did want to go ahead and introduce you to theorem 4.2.2. And it's talking about providing a useful way of creating a new subspace from known subspace. So here theorem 4.2.2 says if W1, W2, all the way through WR are subspaces of a vector space V, then the intersection of these subspaces is also a subspace of V. So that's cool. So just wanted you to realize that you can use these known subspaces and you can create a new subspace from their intersection. So you can see the intersection of those particular subspaces here in the figure, if that helps you visualize it. So like I said, you're going to want to kind of take note of this theorem as well. And where would we be in any chapter if we didn't address homogeneous systems? So please take note of theorem 4.2.3 as well. So hopefully you recognize this AX equals 0. But in any case, the solution set of a homogeneous system, AX equals 0, of M equations in N unknowns is a subspace of real space, or Rn. So I hope you recognize that from previous sections, and it's coming back into play here when it's talking about subspaces. So just realize that the solution set of a homogeneous system in N unknowns is actually a subspace of Rn, and we generally refer to it as the solution space of the system. So that's just kind of a general term for it. So the solution space of the system. So if we look at example 13, here they're asking us to find the solution spaces of homogeneous systems. So don't forget that's in the form of AX equals 0. And I hope you also remember from your previous section that A refers to our matrix when solving a lot of these. So if we look at part A and we wanted to find the solution of this particular linear system, what do we got to do? We got to reduce this matrix here. So this is really easy on us because if you notice, row 2 and row 3 are proportional to row 1. So this reduces very, very quickly. So here you have 1, -2, 3. So this second row would be -2 times the first row added to the second row. You'd end up with all zeros here. This third row, you'd be multiplying -3 times the first row and adding it to the third row, and you'd get a row of zeros here. So that eliminates things really quickly, so we're left with this top row, and so then in this point we have x minus 2y plus 3z equals 0. And then I think hopefully if you guys remember from there, how would you describe that solution set? Well, here hopefully you remember your parametric equations. So basically you would say that x equals 2y minus 3z, and we would assign some parameters now. So we would say that, okay, well, y equals s and z equals t, and then that means that x is going to equal 2s minus 3t. So this would be your solution to this linear system in terms of its parametric equations. The other thing too is you would know that this would then be a plane through the origin. And then don't forget what you've also learned too is that you know how to find the normal too. So this would actually have a normal of taking the coefficients of this of 1, -2, 3. So now you're kind of bringing it all together.